office, please? Kevin to the main office?
I can't believe I start a video and there's an announcement over our PA. Anyway, welcome to AP Physics with Mr. O'Hagan. Today we're going to talk about momentum. M-O-M-E-N-T-U-M. It's also a spelling lesson, momentum. Momentum's kind of this crazy thing. All right, so the way we're going to define momentum, let me move that out of here, is, first of all, the letter used for momentum is, can't use an M, that's taken. It's a P. Whatever. Has to do with Newton and what it was originally called, and the name got changed. Okay, momentum is mass times velocity. All right, which is kind of a weird definition because there are things, particularly light, which has momentum, but it has no mass. Sorry, it has momentum, but it has no mass, which is just bizarre. That's how bizarre light is. And it could be that momentum is more fundamental kind of like idea than mass actually is. All right, yeah, just some things to think about. Throw that in your brain. Anyway, momentum is a vector quantity. There's direction to it. So the direction of the momentum is always the direction the object's moving. All right, so that's it. Momentum, nice, easier thing. This is what's called linear momentum, because velocity is a linear velocity. At some point, we're going to get to angular momentum. That's a whole other fun thing. Okay, remember I said that momentum's actually maybe more fundamental than mass? Well, it just turns out that Newton's second law didn't talk about masses and acceleration. It talked about momentum. So here's Newton's second law, the way he actually did it, okay? So Newton's second law, and this is like for real, F-O-R-R-E-A-L, all right? No longer lying to you out there, all right? Here it is. Here's what he said. Force net is equal to, and I'm going to do it in calculus because, you know, we're a calc thing, dP dt. The net force was the first derivative of momentum. So it takes a force to change an object's momentum. All right, so let's take this idea and let's see where it comes out. Okay, so force net. All right, and we know there's direction, so I'm not going to worry about that right now. Okay, equals d dt. And what's momentum? Momentum is mass times velocity. Excellent. All right, now usually what we do is we assume mass is constant and we pull it out. So it's mass times dv dt, which is mass times acceleration. So what we know to be Newton's second law, what we think we know to be Newton's second law, what we've learned to be Newton's second law, net force is mass times acceleration, is really a special case of Newton's second law where mass is constant. All right, you could have in this, you could have the mass actually changing, so some time rate of change of mass. You could have the velocity changing, or you could have them both changing, and a net force is required to do any of those kind of things. Anyway, so let's do this. F equals net, N-E-T, equals M-A is second law where mass is constant. All right. Anyway, so there we go. That's momentum. We're not quite done yet. Okay. So there's momentum. But now let's talk about momentum of a system of objects. O-B-J-E-C-T-S. I got to get a new purple that's not so thick. Okay, so now momentum of a system of objects. So we've got lots of objects. All right, and we kind of did this before. We had center of mass of a system of particles. No, we had center of mass of a system of particles. Then we had Newton's second law for a system of particles. Okay, so now we're using a system of objects, think of particles, objects, whatever. I don't care. But here's the idea. All right, P. Now this is suddenly a capital P equals capital N times V, center of mass. All right? Now, I'll explain what this means. This is momentum of system. That means add all the momentums together. This capital M, and I used a capital M when we first started talking about center of mass, when you divided by total mass. And then I backed off it because my capital M's, my lowercase m's look alike. Anyway, this is total mass. Basically, here's the idea. If you have a lowercase letter for a variable and then you expand it and suddenly it's an uppercase letter, really that now means same idea, but for a system of particles, for a system, for many objects as opposed to one, for all the objects, for all the masses, however you want to look at it. Okay? So then, Newton's second law for a system of particles suddenly becomes force net equals d capital P dt. And of course, it's a vector equation. All right, so that's momentum in a nutshell. The most important thing to remember is momentum is mass times velocity, okay? And that's the way Newton's second law actually got defined. And then we can expand it out, of course, into many objects and stuff like that. All right. Okay, that's it for momentum. I hope you enjoyed this. You probably didn't, but that's okay. Adios for now.